Find alpha b, the approach angle of the wave when the wave breaks. In this problem, we are provided the deep water wave height, h0, the period of the wave, t, and alpha naught, which is the deep water approach angle. The problem asks to find alpha b, which is the angle between the crest line of the wave and the ocean bottom contours when the wave breaks. To find alpha b, we'll use the relationship which relates alpha b to alpha naught, lb, and L naught, where lb and L naught correspond to the wavelength for the breaking condition and deep water condition, respectively. After solving for alpha b, we can plug in the value of alpha naught, which is 30 degrees, and was provided in the problem statement. But we still have left to find lb and L naught. L naught equals g times t squared divided by 2 pi. Variable g represents the gravitational acceleration constant, and variable t is the wave period, which was provided as 15 seconds. This makes L naught equal to 1,151.645 feet. Lastly, we need to determine lb, the wavelength of the wave when the wave breaks. We know we have found lb when we select a wave depth d, which results in a wave condition where the actual height of the wave, ha, equals the breaking height of the wave, hb. This is the same comparison as if we happen to divide both sides of the equation by the wavelength, L. To begin, we'll arbitrarily choose a wave depth of 20 feet for our first iteration. Next, we'll compute d over L naught, and after plugging in the appropriate variables, d over L naught equals 0.01736. This value of d over L naught corresponds to a d over L value of 0.05353. Therefore, the wavelength for this wave at a depth of 20 feet equals 373.622 feet. Also, by knowing the value of d over L naught, we can interpolate to find the hyperbolic tangent of kd and the Scholling coefficient, h over h naught prime, where the variable h represents the actual height of the wave, ha, at the tested depth of 20 feet. And that variable h is what we'll use to compare the actual height, ha, with the height of the breaking wave, hb. The right-hand side of this equation, hb over L, equals 0.142 times the hyperbolic tangent of kd, which equals 0.0460. Solving for the actual wave height, ha, we must first compute the approach angle the wave would make at a depth of 20 feet. And after plugging in the known variables of L, L naught, and alpha naught, the crest line of the wave would be 9.319 degrees offset from the ocean bottom contours. With this value of alpha, we can compute the wave refraction index, Kr, which equals 0.9368. After that, we'll compute the unrefracted deep water wave height, h0 prime, by multiplying the refraction coefficient by the deep water wave height. We just computed the refraction coefficient, Kr, and the problem statement provides the deep water wave height as 20 feet. This makes the unrefracted deep water wave height equal to 18.736 feet. Now, we can find the actual height of the wave at this depth, and we'll multiply h0 prime by the Scholling coefficient and the actual height, equals 23.705 feet. When divided by the wavelength L, the quotient HA over L equals 0.0634. Since the actual height of the wave, HA, is greater than the breaking height of the wave, then this wave does not exist because it broke at a depth deeper than 20 feet. For our second iteration, we'll use a depth based on our previous depth and the variables HA and HB. After plugging in the appropriate variables, our next depth to test will be 27.58 feet. When using the depth of 27.58 feet and performing the same calculations as the first iteration, we compute the values shown here. At this depth, we notice the actual height of the wave, HA, is less than the breaking height of the wave, HB. Therefore, our subsequent depth, D3, will be shallower than 27.58 feet. For this next depth value, we'll try 26.09 feet. After running through a third iteration, for our new depth value, we again calculate all the same values as shown. As the actual wave height approaches the breaking wave height, the actual approach angle converges on the approach angle for the breaking wave, alpha b. The approach angles for the first three iterations are 9.319 degrees, 10.899 degrees, and 10.613 degrees, where 10.613 degrees is the most accurate approximation for alpha b, because this value in our algorithm converges to alpha b. When reviewing the possible solutions, the correct answer is B.